Okay. Well, while this is like reloading and everything and trying to make again, I'd like to know. Well, first, obviously, I have to introduce myself, but okay, just a sec. So I'm Alberto Ponte, and I'm software engineer, neuroimaging engineer at QMENTA, which is a Barcelona-based neuroimaging company that aims to build kind of the Google Drive, you say, of neuroimaging in general. And the idea is that you cannot not only store information in this cloud platform, but also process it, analyze the metadata in the same browser, conduct studies, multi-site studies. Okay, now it's actually loading. And this talk is meant to be, well, this tutorial is meant to be kind of an introduction to everyone that is not so much familiar with neuroimaging, or on the other part, for those who are not so familiar with computing in general or coding. So in order to adapt my presentation a bit to you, I'd like to know a bit, like, which one of you are familiar with Linux, Bash, Python? Okay. And I guess that all of you, or some of you, have some neuroimaging, neurology background. Okay. Okay, I know that it's kind of, I mean, who's an expert in something, but, oh my god, this is not loading. Paolo, could you just say, because I'm not being able to connect to the Wi-Fi. I mean, I can use the smartphone, but not. Sorry, what? Yeah. Yeah, I tried that one, I tried the Vitalis one, I tried Telegram, and I mean, I started to emulate my laptop, so I restarted it. Let's try it again. Yeah, no sé por qué está fallando esto. Ya, bueno, sí, podemos evitarlo mejor. Sí, pues, no sé. Se me queda como conectando. No, esto es una copia también que tengo de la presentación. A la cual seguramente no me dejará acceder si no tengo internet. Vamos a probar. Bien. Another question, which one of you are familiar with Docker or Linux containers? Okay, then this will be useful. No estoy seguro de conectarse. Ok, voy a reiniciar la tabla. Vale, para la presentación del drive, sí. Sí, yo voy a conectar el línea para el otro. No, pues también en Google Drive. Abrimos en Google esto. A ver. segnarlo. Cavoli, non ho tanto come segnato. Ne sarà poi. Ah. Perdona, sì, sì. Perché ti viene dopo tornare a casa prima? Sì, adesso. Guarda questo, quindi che la devo fare per appunti che c'è. È stato spiegato? Sì. Ok. Oh. Is there a way to hide the rocker bar? Because I want to click something that is behind. Ah, there. Okay. And this should be on my screen, but I don't know how this works. So, how can I change the layout distribution in Max? I'm not that familiar.
You are an engineer, right?
No work.
Me acuerdo de ¿Tú aquí le tomas pantalla?
Sí, bueno, diferente aquí.
Diferente.
Sí, no. Madre mía. ¿Cuánto puedo? No. Okay, I think it's just inconvenient to have this way, so I'm just going to skip it and present it the regular way. Sorry for the delay. I was trying to make it a bit more dynamic. If you have just a question, raise your arm. It will be just simpler. Okay, so as I was saying, I'm a software engineer, a neuroimaging engineer at QMENTA. And you can, okay, these slides are filled with links and references to tutorials, to documentation about neuroimaging tools, to how to actually participate in our challenge. So if you want it to have, and I really recommend it, you can go to this link. We should give you the slides. Okay. So as I said, this presentation is going to be distributed as follows. First, I will explain a bit what are the common neuroimaging modalities, the ways we have to actually examine the brain, get information from it. Then I will continue explaining why is that difficult, what are the typical problems related with that, and how can we tackle it. And then I will present the QMENTA challenge for those who are already familiar with Python, Docker, Linux, and all these coding tools so that you can start right away. And then I will proceed with tutorials so that everyone, regardless of your background, can actually participate. And I will start with the very basics of Bash, of how to interact with a Unix-like command interface. Then I will proceed with what is Docker, why is it super useful nowadays, how it can help in to reproduce results, to share your computing environment with others so that others can run your algorithms. Well, the other way around, but it's kind of mixed altogether because we are going to be an environment in Docker to run the bash commands. And then I will continue with Python, simple examples in Python, then a bit more elaborated, how to plot things, how to actually build simple regressions on data, and then even some example of a simple neural network to feed the data, to make a predictor so that you can participate in the challenge. I will end this part by explaining how to add your tool in case you want to participate in the challenge to the QMENTA platform, which should be super easy. And if we have time, I will explain how to actually write Docker files, which is a very simple syntax to build reproducible computing environments. Okay, let's start. We want to get information from the brain, obviously, and there are many ways to do so. All of them have its pros and cons, and one of the first, probably in history, was to just place electrodes in your scalp. This is known as the the EEG, we call it the electrocortical. I just need water. EEG. Yeah, let's stay with EEG. And the idea is that this way you can measure kind of the average voltage of the brain is producing on the scalp. And since the brain functions in a kind of oscillatory way, so there are patterns, and you can actually have these patterns. I don't want to get too much into the details of EEG because I know that there's a talk later into that, and he will explain much more and with more knowledge than the one I have about this modality. Okay. Let me just go back to the distribution of screens I had before, because otherwise I have to be turning a screen all the time to know exactly what is on screen, and it's not convenient at all. Okay. Jose, could you please help me with this? Sorry. I'm just such useless in Mac. Just to put the screens again without the data.
¿Quieres poner?
La misma.
En los dos lados.
Sí, como estaba. Perdón. Intentaba hacer lo de las preguntas dinámicas, pero luego se ha quitado la pantalla completa.
Vale. Voy a intentarlo.
Sí.
Lo tienes ahí.
Sí, está. Sí. Okay, the next procedure, because it's a procedure, actually a surgical procedure, usually, is to place electrodes inside your skull. That is in direct contact with your cortex. This is obviously not something you want to get done just by the fact of science. Well, if you're crazy, you might, but in general, you just want to do it in case you really have a need for it. The electrocorticography can be really useful to build artificial limbs for people who have lost an arm, a leg. So you can just place electrodes, for instance, on top of your motor cortex, and then you can map your activation of the neurons in those regions to actually move specific members of your body. And obviously, at first, this is not as easy as just like plug and play. But this is something that, with a lot of experiments, with a lot of trials, the body can actually learn to do. And now, like, there are many examples of people who have been operated with one of these arrays of electrodes, and then they can just do something that it was completely science fiction before. Then we start with the proper neuroimaging in the sense of what is applied in most cases in the hospitals. The first one is the typical computed tomography, which is kind of an X-ray done at many layers that produces a three-dimensional image. This can be super handy if somebody has a trauma, or if somebody needs a fast scan. So doing a computed tomography is something that you can do really fast. You can super easily see if there is any kind of foreign body, any metallic body inside the brain. And in general, it can be used a lot also for if there is a stroke. You can see the clots, the blood vessels that have been traumatized or either just coagulated in your brain. Then we come to the magnetic resonance imaging, MRI, which in itself has many modalities. You can see here a comparison video between computed tomography and different modalities of MRI scan. The principle of MRI is very different in the sense that it's not light, which is just like X-rays going through your body and like touching a receiver, but instead you go inside a tube that has a strong magnetic field that basically aligns all your atoms, not your atoms, but like most importantly the hydrogen atoms, so that their spin of these atoms coincides with the direction of the magnetic field. Then just by emitting like radio frequency pulses on a perpendicular axis, you can get an echo. And depending on the time that it gets to you, like the time that it takes this echo to get back to you, and the time that you wait until like to listen, or the strength of the frequency of the radio frequency pulse that you send, you can get different sensitivities for different kinds of tissues. And that is why MRI, it's in kinds of a structural analysis, is not only one kind of image, as would be for the computed tomography, which is in real it's not, but it's much easier to explain this way. But you can get different kinds of images depending on how do you tune the machine to work. So in these cases, we can see that a T1, T2, which are like the most typical, well, with FLAIR also, kinds of acquire images in MRI scanner show a lot more details of the brain than what would a CT do. But obviously MRI, it's not something you can always do because it takes a lot of time. While a CT can be done in 20 minutes, even less, an MRI scanner can take up to hours, especially if you need high resolution. And it's not something you can do just if somebody hasn't had a car accident and you want to see how is the brain, because you cannot just put him into a tube and wait for several hours to finish the exam. Obviously, also, you cannot use it when there is a risk that a metal object has been placed inside, because remember that you're using a giant magnet. And there are sadly many cases that happen in history where people just entered the room with a fire extinguisher or a metallic object, and obviously it didn't end well. Because you have to remember something, that the MRI machine, the magnet is always on. It's not something that they just turn off and on depending on something is inside. The magnet is always on and can only be switched off like in case of an emergency, and then getting back on. It's not something you just by pressing a button. It's something that really thrashes the machine. So think about it. You have a room where no metallic object can be, and obviously this is dangerous to manage for the hospitals. MRI scanners are super expensive. They start, well, okay, the resolution of MRI scanner depends on the strength of the magnetic field, and those are typically 1 Tesla, 3 Tesla. Now we are starting with 7 Tesla, but a 3 Tesla MRI scanner can cost around 400,000 euros or dollars to hospital. So it is something that they don't can have many of, and literally people is competing for the time to get the scanner. So obviously this has its caveats. As you can see here in the description, why it's not presenting again? Anyway, I will continue this way. MRI is super useful for neurological disorders. You can actually see atrophy in the brain for people who have different kinds of neurological disorders, or you can see the tumors. And what MRI scanners produce basically is the same as a CT, which is just a set of voxels. That is, if a pixel is in 2D, a voxel is in 3D, and it is just a 3D reconstruction of the brain. And the way how you handle this data can be really susceptible to errors, because as I will show later, an MRI scanner is not something that always produces the same result. It can change a lot. Even the same patient, 2 times, 2 acquisitions, different days, can produce like super different results. And that's because there is a huge problem with the signal-to-noise ratio of these kinds of scanners. And obviously, as I said, since the scanners are really expensive, hospitals cannot have the latest. It's very common that you will go to a hospital and you'll get an MRI scanner of your knee, and then you will probably use a scanner from the, well, not the 90s, but almost, you know. Another modality is the fMRI scanner, which can be taken by the same MRI scanners, but they are meant to do something completely different. An fMRI scanner is meant to analyze a function of your brain, not the structure. So basically, it's something that you scan for a period of time, and you get a signal through time. But the signal you get is not the electrical signal, because there's no, well, there's kind of ways, but the best way for MRI to get what is happening in the brain is to analyze how the hemodynamic response changes in the brain. That is, how the oxygen changes, increases or decreases in your blood vessels. And this is basically what the fMRI scanner captures. This is a very nice example here, which is basically a very famous study where there was a guy, a girl or guy, I think it was a guy, who basically was in a minimal conscious state. So it is typically what we call a vegetative state, but it's definitely better to call it minimal conscious state, because vegetative, sometimes we imply that the people is not aware of anything, but sometimes they are conscious, or they are partly conscious. And the thing is that because they cannot move, or they cannot just even move their eyes, we just simply think that they are no longer there, but they might be aware actually. And one way to prove this is by placing an MRI scanner, doing a study first on people that are healthy, and saying, okay, when I ask you a question, if you want to answer yes, think of playing tennis. And if you think, and if you want to answer no, think of staying at your home, resting, something like that. And then you analyze what is common in all these signals, and you apply it to somebody that is in a vegetative state. And you ask him a question, like, is your name John? And you explain the rules. Think about playing tennis if you want a yes. Think about staying on your house if you think no. And then you realize that these people is actually answering to your questions. So these people, not always, but sometimes they can be actually awake. And obviously, being aware of this is something that, in the common sense, it's necessary. And that is why the study of neuroimaging in general, it's so necessary. Because sometimes we apply rules to our society based on only what we can observe. And it's so important to realize that there's much more happening there. That not somebody is crazy because of, I don't know, his conduct or his way has been born or anything, but rather because of some condition. And the same happens to people who is just, oh no, he's in a coma or he's in a vegetative state, which are completely different things. And sometimes we have to know more society about this. Another way to actually analyze the currents that happen inside the brain is to use MIG, so magnetoencephalography. And basically what this does is literally analyzes the magnetic fields that are created by the neuronal circuits of your brain. The only problem with that is that the brain magnetic fields are really, really small. So they are in the order of femtovats, I think. And the problem with this is that those machines are super, super sensitive. And obviously, you have to place them inside rooms which are super isolated from the outside so that no magnetic field can enter. And even then, the signal that you get is not so important in the sense that it's not so relevant, and it's super difficult to analyze it in the sense that you might never know if really it's something happening in the brain right there, or it's just some noise that happened to be in the machine itself. It's interpreting the results. Obviously, this is an exaggeration. MIG can be really useful, but I just want to understand that it's not something that's already solved. Again, just I was forgetting about this. MIGs are typically used to analyze activity through time, the same as fMRI. So you don't get a structural image, but rather something that happens through time to see what's happening in the brain when you perform a task on where you are just thinking about something. Then we get to the positron emission tomography, which basically consists on injecting you with a tracer, a radioactive tracer that emits positrons when it is metabolized by your body. And it is also a signal of what is happening in the brain through time, but in the sense of the overall energy that it's being consumed, used by the brain at any time. You can see here many different cases of a PET scan regarding different conditions. So for anesthesia, after recovering from anesthesia, vegetative state, you can see curiously that when you are in a rapid eye movement, sleep, the brain is getting more energy than in other cases. You can also see that brain death is completely black, and that's because when somebody enters brain death, this is not something like vegetative state. Brain death is dead, and there is not a single case in the whole history who has recovered from brain death, because basically you have lost the structural integrity of your brain. Okay, so the typical problems with this data is that it's super noisy. It is also that the brands that create the scanners do not deal with the data the same way. They produce data like metadata that's different. So there is not a consensus. There is not a kind of common ground. Although there are standards, those standards are really ambiguous in the sense of format. For instance, the DICOM format can have literally hundreds of thousands of tags that is different fields of information. And obviously what happens in the end is that every scanner of every brand fills just one of these tags. So then you end up not knowing what to actually search for when you are trying to automatize the analysis of this data. Another thing is that it's not very easy to get a lot of data of this, as scanners take their time. And especially if you want data from a PET scan or from other modalities that require you being injected with a radioactive tracer, you might not get so many people wanting to just do it, especially if they are healthy. No, everyone, when they have a condition or something, they want to get a scanner. They understand the risks. But how do you compare with healthy subjects when healthy subjects are typically not, well, so much into getting radioactive material into their body? And obviously, as I said before, that hospitals do not have the latest equipment because it's really expensive. Here you can see a typical problem with MRI data. This is a T1 structural image from an MRI scanner. And you can see that the original image, which is in the top left corner, has some kind of gradient, which is produced by a low frequency signal emanating from the machine itself. So the machine itself contaminates what it's getting. You can see here that this is a typical processing step of many analyses of neurological data, which is to compute the bias field and then subtract it so that you get an homogeneous image that then you can do for later analysis. You can use for later analysis. You can also see here that another step has been taken place. And the thing is that so we have removed also the skull stripping. It's how it's called. And this is obviously necessary to just deal with the brain and not with the characteristics of every person, like every person's skull. And finally, it's just that there is a lot of bureaucracy with medical data. People know that there is really, really valuable, and people know also that the data is just something that companies want, and not only insurance companies, obviously, but a lot of companies. But insurance companies can be something really tricky, because what happens if you put a lot of data out there with the brains of everyone, the lesions, that then you try to get maybe insurance for your health, and then if I was in a company dealing like insurance, healthcare, I might be interested in knowing if these people is prone to have cancer. I might look at their parents. So this is obviously something that has to be protected, and it is well protected, but there is also a lot of bureaucracy that has been grown for a lot of time, and that has not caught up with recent developments in informatics in general. Okay, so QMENTA basically aims at getting rid of all these problems in the sense of just providing a unified solution. As I said before, we aim to have some kind of Google Drive for neuroimaging, when hospitals, basically can upload their data, and then this data can be shared easily with other researchers, where you can just plug in your analysis, your processing, your algorithms, and then just say, hey, I just realized that doing this is much better to analyze whatever, and I can just share it with your mail by just writing your mail, and then the other person will be able to just run it without having to install all the programs required in your computer. So now I'm going to show you a bit how is the platform, so that you can better understand also how the challenge that we're proposing fits with this. Okay, I'm going to go to the platform, platform.qmenta.com. And I'm going to enter my credentials. Okay, let me adjust this to the screen. So this is the main menu of our platform. And what we have here is multiple projects. Projects can be private or public. When they're public, everyone can have access to them. It's like public databases that we gather and put all of them here, so that people don't have to download all these files, but they can just rather refer to here. You can also download files from here, but the intention of here is to have a unified place for all these databases. Then you can easily see what is in this study, in the sense of analysis that have been performed, the data that is in there. You can browse through subject sessions and see the input files for every one of these sessions, the analysis that have been run for all of them. Obviously visualize all this data in the browser itself without having to have any specific computing environment. Well, if the internet was a bit faster. Okay, well, you get the idea. This is going to load a T1, and then you can browse through the slices as any other viewer. Okay, getting there. All right. Just a second. Okay. For some reason, that file was not loading properly. So here you can visualize the data going through the slices in the 3 planes. as any other viewer, just in browser. Then another kind of nice feature of this is that you can, depending on your study, you might want to conduct some, well, statistics on this without having to fetch all the data and do the scripts yourself. So if we go, for instance, to, I don't know, I will just pick one of the projects and then go to the data, and then you can do here project quality. This will show you what's distribution for this study in itself. You can see that 378 of the subjects in here have like T1, for 40 ones per scanner actually, and the others only have 3 T1s. This can be super useful when you're conducting studies and you realize that, well, there is some inconsistency in the data. The same for the resolutions. We can have here, you can see here that there are 81 files that have no resolution specified, although this could be because some of these files are just TXT files or CSV files that people upload to the project. You can also see metadata statistics, super easily cross. For instance, if you select one of the fields and if it detects that this field is a number, being data float or integer, you will see automatically distribution of ages for this study. And then you can, I don't know, pick one of the indices for this study, and then it will automatically compute the regression for this data, although for obviously in this case, it's not very representative of the information that I selected. And then you have the analysis themselves. So this connects with the challenge. What we are going to do is try you to make a tool that it receives a subject's data, it receives a subject's T1, and it computes their age. It guesses the age of that patient. Your analysis is going to be launched as any other analysis, which is by selecting one of the subjects and then selecting one of the tools that we have. And then it's going to output the age in a text file. I'm going to explain this later in a bit more detail. If I go now to, let's go back to the demo study. You can see here the analysis that have been run on this study. And these analyses, they typically compute two things. One is a report, and then all the list of output files for this analysis. For instance, if we run ANS, which is like an open source normalization tool for MRI images, structural MRI images, you can see here that this analysis has produced all these results, which are segmentations of the brain, which are CSVs with the cortical thickness of all these regions in the brain. And then you can see that it also produces a report, a PDF report with all the results. And you can also see directly the important results by clicking inside. And this will eventually load the segmentation and the cortical thickness for this patient. So in the end, it's just all about automatizing the processing of all this analysis and making it faster for researchers to just plug in their tools and reach hospitals and other research institutions easily. Here you can see segmentation. So it's basically putting a label that it's color to different regions in the brain to identify them. In here you can see some kind of heat map about the cortical thickness of different regions on the brain that you can then download as CSV again. So getting back to the challenge. Okay. So what we want is basically to predict the age of patients. Obviously, to do so, we are going to give sessions with age. This means that you'll have access to a data set that will have 1,000 subjects. All of them will have a T1 image, MRI image, and all of them will have their age in years. We do it this way so that you can train any model that you want to this data, and then we will evaluate against some unseen data that you will not have access to evaluate which one of the models performs best. Of these 1,000 patients, only 100 are available today, and we are going to be adding more until we arrive at the national hackathon, so that not all the data is available from the beginning, and so that you people do not have too much advantage against compared to the people who is participating only to the hackathon. And there is a bonus challenge in this one, which is find the approximate 5% of patients with Alzheimer's disease. We are going to send you the slides later, and you'll find that in the notes of every one of these slides, there might be some links, and these links actually can point you to papers that discuss how to actually tackle these problems. So as I said, the assessment is going to be just compared what your tool produces, so the age that your tool predicts against some unseen results, against some unseen T1 images, and then also there will be a bonus for the ones who detect Alzheimer's patients, and there will be a punishment for those who detect false positives for the Alzheimer's patients. As you can see here, there is an additional prize if you participate, or if you submit inside the National Hackathon that's going to happen the middle of the month next week. There's going to be a 1,000 euros prize for the winner of this challenge, or for the team that wins this challenge. And there's also the possibility of collaborating with us in doing a publication, in trying to approach hospitals, research institutions with the algorithm if we really believe that it can be useful to them. Obviously, you will retain the intellectual rights and all of this. We are not just trying to appropriate from your ideas. This is not the point of this challenge. So in a nutshell, your tool will receive a T1. You will have to implement a tool inside a Docker image that I will explain how to do it later. And this will produce a text file with two fields, which is like the age and an optional letter, which will be age or two letters NH for healthy or non-healthy if you detect Alzheimer's or not. In order to submit your tool, you will have to create an account to Docker Hub and then just push this Docker image. If you're not familiar with Docker, don't worry, I will explain it in the tutorial later. And then you can follow the steps explained here to add the tool to the platform, which is basically just putting your name, like how is this tool going to run, and the URL where you have submitted this Docker image with the tool. And then we will expect from you a mail explaining what is your approach. It can be really brief, as I said here, but plots of how do you actually model data will be really appreciated. And if you want to start right away, you can just go to the platform, QMENTA, and register with this code, which will grant you access to both the dataset and access to the My Tools menu, which is the ability to actually add tools to the platform so that you can run using our computing infrastructure instead of your computer. I want to emphasize this because, as you will see, many of the neuroimaging tools can take a long time to process. And when I mean long time is that even with modern computers, it can take up to 10 hours of computing time. And if you have 1,000 subjects, you obviously do not want to run the analysis yourself because you will not end in the whole of your life. And that is also one of the reasons why we have the platform, actually, which is like to automatize this processing and also to make people share the results of analysis. If there is a researcher who has run the free surfer pipeline on some data, then why another researcher has to run the exact same pipeline again? This is not useful. If it's inside the public project, they can share those results. They can be used as a starting point, which is just in a general sense a way to grow faster in the community. Okay, so now I'm going to start with the tutorial itself. I'm going to start with the very basics of Bash, which, well, as I realize many of you know. Which one of you have never worked with Bash? Okay. Okay, then I will explain. This is meant to be the following way. So what I would like you to do is install Docker if you have your computer and you want to actually try it yourself during this time. If not, it's okay. I will just grab my computer and put the screen here and do the demonstration myself. But I think it would be really useful if you could follow with me, try everything, because it will help you understand better how to run this. So first, there has to be a brief introduction on what is actually a container and why is it useful. You probably already know what is an operative system, which is Windows, Ubuntu, or Mac OS. The idea is that an operative system manages your hardware, and it is the place where you install libraries and then you run applications on top of that. This, whilst is the fastest approach, obviously, because you don't have any kind of layer in the middle between the libraries and the hardware, can also have its problems, because in time programs tend to be incompatible with between them, and then you end up with libraries that are no longer shareable. You cannot install, depending which program you have another, and this is particularly difficult if you're not in the mainstream world, in the sense that if you work in computing for specific tasks, you end up realizing that the effort in homogenizing that is not as big as it is for other kind of applications. Virtual machines are OSs that you can run inside another OS. So it is what you achieve by running, for instance, VirtualBox or VMware, which are programs that allow you to emulate a computer inside a computer. So you can run Linux inside Windows, or you can run Windows inside Mac, for instance. And these, whilst they're really, really useful, they have quite a huge caveat, which is that the performance is lower, that they take a lot of time to install, and that they're really not portable. You're doing an installation on your computer specifically, and it takes a lot of time to start up, because if your computer is slower, like the virtual machine is going to be much more time, like a lot more times slower. So then containers come into play, and what we have basically, it's very similar to virtual machines, but in this case, the kernel, which is the part of the operating system that in virtual machines would be like different for every virtual machine, in this case is shared across containers. And what this means is that you can run applications with their libraries compartmentalized, completely separated, but they will not have an impact on the performance. So you can run them as fast as if they were in your computer. The only problem is that it's not as flexible as running virtual machines, because you have to run them on the same kernel. But companies like Docker are now providing ways to do so. So you can actually run now Ubuntu Docker images on Windows, although it's still a bit new, and you need, for instance, the Windows professional versions and with one of the most recent updates. But it's possible, and we're getting there. Docker. So Docker has a series of very basic commands, which are these ones, and what they provide you is a way to save the state of a machine in an image. And when you have a Docker image, you can just publish it online or save it in a pen drive, literally, and copy it somewhere else. And it is a way to transfer all your setup that you have for your computer to somebody else. It is also a very nice way to distribute your applications, knowing that they work, because if they work for you, are going to work for anyone else, because they contain everything they need inside these images. So now what I'm going to do is plug the other screen and start with the tutorial itself. Okay, there. So as you can see, I'm running VMware, which is a virtual machine, to show you how to use from Ubuntu or another Linux system. And inside that one, we are going to be using Docker to create computing environments and to show all the examples. Okay. I'm going to be putting the slides here so that you can follow with me. Can you really read or no? Okay, then I'm just gonna continue myself. Remember that you can see this slide by going to this link. It's gonna be much useful this way, because otherwise I will not be able to show you the slides whilst typing the commands itself. Okay. Okay, so what is Docker? What is it useful for? The idea is that I'm in a terminal and I need a new computing environment to install some software, but I don't want to contaminate my computer. I want to be in somewhere that I can control and then just copy it to somebody else. So let's say I want to start a machine. This can be done by the docker run command. I want it to be interactive, and I want it to be with a terminal so that I can write commands in it. For now, we'll just use the basic example. So I will just grab another operative system. And I know that, for instance, Ubuntu has a very small image, so I can just type Ubuntu. Boom. I'm already inside another operative system. And if this was run in a Mac, now we would have a completely separated environment, which is able to run Debian commands in the sense that you can install anything that's compatible with Ubuntu. You can also run any script that is compatible with Ubuntu. You can install anything, and then you can just save this and send it to somebody else. Containers can be run in the background. You can detach from a container by pressing Control-P, Control-Q. And the idea now is that this container is going to be run just as a background process. You can do Docker PS, and this is going to show you the running containers. Sorry. There. And you can see that we have a container. Still does not fit the screen. Okay. Now it's better. So we have a Ubuntu container running the command bash, which is the shell for the terminal, if you want to call it, although it's not the same for Ubuntu. That was created 1 minute ago. We can reattach by just running docker attach and the name of the container. Container, if you don't specify it, it will assign a random name, which in this case is Awesome Brown. And now we're inside it again. You can install programs as in any other Linux system. You can just do apt update to get the list of programs available. Although since I do not have internet, this is not going to work. And then you could install anything by just typing the name of the program as any other command. Then when you want to store the contents of this container in an image, you can just do docker commit, then the name of this container, which is Awesome Brown, and then the name of the image that you want it to give. So config, I don't know, 1. Now if I run Docker images, this will tell me that I have a static copy. I have a blueprint of this configuration environment in an image. An image then is something that I can just send to somebody, and this person will be able to create a new machine from this instantaneously. So it doesn't have a startup time. You can see that config1 is an image, so it's not something that it's running. It's rather something static. And it has a size of 79.6 megabytes. Images can get really large, obviously. The image that we have prepared for the challenge, since it contains a lot of neuroimaging tools inside, it is like almost 7 gigabytes. But it is a full computer in the sense that you will have ants, you will have other tools inside, and you can just use that to participate. Okay. Then, As I was saying, the basic commands for Docker imply the managing of these images and the managing of the containers. You can run attach, you can detach, you can list the processes, stop a container, remove it, remove images. You can also copy files from your host computer to the containers by just running docker cp and the source and the destination. You can start a container with a mounted directory. This is a shared directory with a v option. And then you can just run another command on a pre-existing container by using docker exec. You can also rename it. So now, bash. Come on. What is bash? Bash is the language that most Unix-like shells use. And by shell, I mean what we're seeing now. That is the command line interface that provides me access to the machine without having to have any kind of user interface on top of this. It can be really handy if you know a bit how to automatize things, because otherwise you will end up repeating a lot of stuff on a typical user interface. And this is something that in time you want to avoid. You want to be as efficient as possible. So the very, very basics of bash include just browsing through the list of commands that you set, which can be done in history. This is going to show me the commands that I ran in the past. I can also move up and down to see the commands that I ran. I can kill process with Control-C, detach from things with Control-D, clear the screen, and show the help. In general, for bash, the most important thing is to know how to show the help. You will never know everything. And the idea is that if you don't know how to execute a command, for instance, ls, show me the contents of the directory. If you don't know the option for ls, you can always just run 2 dashes and help, and this will show me what are the options for this. And now I will just know that I can just use L, for instance, to show me the details of the files or other options to improve the functionality of this. Okay, but let's start with the Python examples and the bash scripting. I will start a Jupyter Lab in the container that I prepared for this challenge. And this will provide me a program to code and to show the results instantaneously without having to be switching screens all the time. Okay, so for this challenge, we have a container that is called QMENTA SDK/bhack. The complete Docker command, come on, to run it is docker run, then I want a terminal inside. I want this container to be called bhack. I want it to be able to work with the port 8888 that have to map inside to the 8888. And I want to use the image QMENTA SDK bhack 18. Obviously, you will not have this image in your computer, so the first time you run this, it's going to retrieve it from Docker Hub, which is an online registry of images. Now you are inside the environment that we have prepared for this challenge, so you will have access to many commands to analyze MRI data, like MRI info, that will show you the headers and the basic information of any MRI data. Inside this container, we place, as I said, a Jupyter Lab, which is a utility to run Python scripts in a very meaningful way. And by that, I mean to show the results as you go. So let me show you. If I run Jupyter Lab to the port 0.0.0, because I want this Jupyter Lab server to work with the internet browser that I'm using outside the container. I don't want to be writing all the time inside this shell script. Otherwise, it's going to be super difficult to get like anything complex done. And since this is running on a root user, which is the super user that has access to everything, IPython would prevent me from doing this, so I will have to add another option, which is allow me to be a root user. This has created a link that I can just copy now and use my host computer, my host operative system, to open this in the web browser so that I can connect to the environment that I have in this Docker container without having to go through the shell. And here are some basic examples of Bash and basic examples of Python. Then an example of how to use our API to get data from the platform without having to click all the time. So using a programmatic approach. And a simple example of scikit-learn to train models to feed some data, which is generic but it's going to be super useful for you if you want to participate in the challenge. Okay, let's start with the Bash script. Bash, even though it's super handy, it can be a bit tricky to understand. This is a really simple script that doesn't do actually anything much that is super useful, but you can see that even with a few lines, it can be really tricky to understand what is happening there. The idea of this script is to show you the different ways you can assign data to variables. So I'm going to show you this in another environment, which is my host computer. So you can assign values to variables in Bash, just like this, which is easy. But then how do you really get the value from X? Because if you run X, this is going to try to run a command called X, not get the value from X. For that, you will have to input the $sign and then put the cloud address to actually refer to that symbol. But this is going to tell you that the 23 command does not exist because it's always trying to run what you enter. So what you want to do to print actually the value, it's to use the command echo. That is, just show me the output of something. And in this case, this will just give you 23. Even though this is super simple, you can see that Bash itself, it's not meant to be an imperative program like language. It's not meant to be something to be used for computing. It's just a command line interface that has some language into it so that you can define functions and you can define behaviors. And what if you want, though, to have the result of some command in a variable? Let's say that you run ls, which shows the contents of a directory, and you want this to be assigned in X. If you do something like this, what is X now? Obviously, X is ls, but it's not the result of ls, which is the result of executing ls. So if you want to actually execute something, you will have to use $ again, but not cloud address with parentheses. And now you will see that echo X, but with the $. And the cloud address will show you actually the result of executing X. With all of this, what I want to point out is not teach you so much about Bash as to make you understand that Bash is not the best way to go in scientific community, because it's a language that has a lot of what's known as boilerplate code, which is code that you have to add just for the sake of the language to make it work, code that it's actually not producing anything useful, but it's just there because it's the way it was built. In this case, this simple example that does not do anything much useful, it's just going to print running a script at, then it's going to execute the command print working directory, which literally just returns you where are you working at. And then what it's going to do is it's going to do a loop for everything that is in a directory. Now, what directory? This is $clouddator1. In Bash, when you use $clouddator and a number, you are accessing the argument that you are passing to the command. What I mean by this is that when I execute a command and I put something next to it, this is going to be the argument of it, the first argument. So if inside a script of Bash that I could just call from the command line, I want to actually access this value, you would use a $clouddator and then a number to refer to which one of these arguments you're getting. So if I run this script with a directory next to it, it's gonna do for every file that is inside this directory, perform this action. And what is this action? This action is just assigning to X the value of X plus something. So it's just appending. And it's appending using a space. But in Bash, if you want to actually use space as a space and not as a separation between commands, you would have to use the dash to mark that the next character is actually a space. And then you would have to actually do something else, which is in this case running a function with this. But what is this? What is fname coming from? It's coming from the loop itself. So basically what it's doing this is, for every file that is in this directory, call this function that I have defined on top of this, just echo itself, so basically just print what you have passed me, and append it to X, and in the end just echo all of this, which is just print all of this. As you can see, even printing the contents of a directory and appending them to a single variable can be relatively complicated in Bash. And that is why Python really shines in comparison and other scripting languages when trying to apply more fast approaches to many problems. So now going to Python, most of you know already Python, no? I think. Okay, then I will start with the basics then. Sorry for those who already know. I know that this might seem a bit basic, but okay, how do I hide this column? There. Okay. So this is an IPython notebook. IPython notebook is a way to execute Python commands and show the results as you go. You can save them as if they were documents, and it is a way to combine text, formulas, and commands in a single file. In this case, I'm going to be executing these cells by pressing Shift-Enter, sorry, which goes to the next cell automatically, so I don't have to be moving all the time. You can see here an example of assigning variables to a number and to a string, and then just printing those values. The type of a variable in Python changes through time. It's not like other languages like C++ or other strongly typed languages, that what they have is that when you declare a variable, when you say A, I'm going to say A is an integer, so now it can only contain integers. Python is not like that. Python can change, and you can see that A is 1 to 3, but then I can just change the value to something that is completely different, which is, for instance, a string or a Boolean in this case, which is a true or false. And then the value of A will just simply change. The type is a function of Python that you can use to actually get that type. Obviously, you cannot do all kinds of operations with variables that have different types. You cannot add an integer and a string. But you can cast, which is basically adapt the type, so change the type by looking at the contents and producing a meaningful result by using this kind of syntax. And this, what it's going to do is take A, which is an integer, convert it to a string, and then append to B, which is an operation that can be performed because A and B are both strings. In Python, you can define lists really easily. You can define an empty list like this and then append values as you go. You can also append lists to lists, and this will produce just the concatenation of all the elements. Is everything clear? Am I going too slow or too fast? It's okay? Okay. Yeah. You can access the values on Python lists like this. The first case, this is going to access the first element of the list. Python lists starts at 0. This is going to access from the second, to the third value, because when you specify an interval, this does not take the limit that you put, but it takes the previous element. So in this case, it's going to take, as you can see here, only 2 and 3, because those are the elements in the list that are specified by this range, not including the last one. You can specify lists, elements access by writing just the last element you want to include, and then it's going to go from the beginning to the end, and you can specify the other way around. Just by putting semicolon to the other side. Sorry. And now you can see that it's going to take from the third element, because it starts at 0, to the last one. Dictionaries are one of the most handy data structures in Python, allow you to store values by specifying a key. This means that instead of having a list where you have to access the values by entering the indices, you can just put a key and then a value. And then you can refer to the value by just entering the key again. So in this case, I declare a dictionary like this. I say that X for John is going to be 1, 2, 3, X for Alice is going to be whatever. And then I can refer to the value of John just by entering the key again. You can define functions, and the parameters are put explicitly here, not like bash. And then you can refer to the value of those functions here. Obviously, as all programming languages, you can define loops or conditions. Here you can see that I define a list which is from 1 to 5, and then I do, for every number of this list, there are 2 ways this can go. One is, if the number is below 3, print the function that I defined before, which is add 1 to the number. Otherwise, just print nope, which obviously produces the result everyone can guess. The power, as I say here, of Python, though, is that it has a lot of packages. It has a lot of domain-specific packages or generic packages that you can apply to almost any problem. And the thing with Python is that if you're tackling a problem and you realize that you're writing too many lines, this is probably because you have not found the package that does it for you. We tend to think that our problems are unique, but the reality is that many of the problems we encounter when tackling simple logistic problems with numbers, with lists, are already been solved, have been solved by someone, and this someone has created the package. Packages can be installed easily by running pip install in your console, or by running pip, which is the Python package manager, install here, and the name of the package, in this case random. Random, however, is a package that's included in Python as many others, so there's no need to install it. And random just produces a random number between 0 and 1. There are many ways you can import packages in Python to use the functions they define. One is by just importing the whole package and then accessing the functions. The other is by going directly to the function that you want or the module that you want and then calling it. And the last one is to assign an alias like this. You can ask for input, as it's shown here. And you can manage almost all kinds of data with their appropriate package. For instance, in this case, I'm showing how to use a CSV file, which is like typical columns and rows file that is produced by any Excel or any spreadsheet program. And what I'm doing is I'm writing directly in a format that then Excel or any other program will understand. So I define two lists. And you can see here that I'm defining list in a different way, which is 50 times A, and the second is the list comprehended in the range from 0 to 100 in a step of 2. Then I'm constructing a table, which is just a list of lists, and then I'm printing the table. So basically now I have a list with 50 A's and a list with values that go from 0 to 100 in a step of 2, not taking the 100 value. And with this package, you can simply just write this data to a CSV because somebody has implemented a package that takes a table and writes it to a CSV. You can see now that this has been created in a CSV file here. Okay. I'm a bit short on time, so I will have to speed up a bit. The real issue with Python in the end is when you find yourself lost in the sense that you don't know how to do something in Python, it is such a general community that you will be able to find absolutely everything in many of the websites that are created by people to actually solve this problem. So you will find that many of the issues you have can be solved in Stack Overflow, can be found in other many. Please do not go to Yahoo Answers. But you will find that everything has been solved, or almost everything, and so that you can focus on the real hard problem and not on managing the data, managing the numbers. Plotting in Python is also really easy. You can use the matplotlib package shown in here. Here I'm just constructing some random data from 0 to 2 in steps of 0.01. Then I'm creating the values for the y-axis being a sinus of some function, and then I'm just plotting the results. I'm giving values to the axis. This is very similar, as many of you will notice, to MATLAB syntax. So it's almost the same, actually. And this produces this plot. And then also to mention that when there are errors in the code, you can catch them and do specific behaviors with the try except clause, which is like if you do something that you know that it might trigger an error and you want to take a specific action. When this happens, you can just use this kind of syntax. Okay, now I'm going to explain how the QMENTA API works. Okay, let me just run this again. Okay, in order to use the API, you will have to log into your credentials. Okay, not convenient. And then you will have to use these credentials to actually get the account access to the QMENTA platform. You can list all your projects that your user has just by using account.projects. This would be much more nicer if I could use the internet to show you the results of all these calls, but I'm afraid this will not be possible. Then you can access one of these projects by just writing the name as shown here. This is the 1000 Brains Challenge dataset. And then here you can print the name of the subjects just by accessing the variable of the project that it's called subjects and getting the 10 first elements. You can access these subjects by entering their ID with a number and then list the input containers for the subjects. The input containers are basically the sessions for that patient. This means that if somebody has taken a scan one day, this was a session. If he was taking another scan multimodal scan. So there is a CT scan, maybe an MRI scan the same day. This will go into another session. You can get the list of these inputs by just accessing the variable. You can get all the subject metadata that has been inputted by the user uploading the data like this. This will typically include the age, the gender, the handedness, and many other clinical scores that might be related with that study in particular. Downloading the data from the input is super easy. You can just use a function that it's called download file, and then you will have to enter the container ID, which is the input ID that was specified above, the name of the file you want to download, where you want to download, and overwrite to true if you have already downloaded it or not. In any case, this is optional. You can use NiLearn, which is one of the packages installed in the QMENTA SDK base image for this brain hack to plot T1s, just like this. And you can just use the package subprocess, which is included in Python, to run commands in the operative system that is inside the Docker container, such as mrinfo to show the details for this T1 scan. Here you will find also a script to download multiple files, which may be handy if you want to analyze multiple subjects and download only specific files for many subjects. And here below you will find also how to get the pre-computed results of analysis from the platform. The idea is that for all these data sets that are being used for this challenge, so for the project of the 1000 T1 scans, we will be running the ANS, the Advanced Normalization Pipeline, on all of these subjects, and the results are going to be appearing gradually during this month. The idea is that you can use these results to basically train any model to predict the age. And the way to download all this information without having to use the platform, if you want, is to use these 3 lines, which just will access the analysis from a subject, get the first one, get the ID for this container, then show me the files that have been produced by going to project, list container files, and entering this ID, and then just printing the files. In this case, you can see that I'm going to print the names of files that ends with CSV. So basically the tables that include the analysis of the cortical thickness, which is what the ANS analysis outputs. And here you can see how to download the file now that I have these names. It's just, as I said before, using the download file function from the project. Okay. Now we'll go to what I think it's the most interesting part, which is basically how can you do even the simplest approach of machine learning to actually know something from this, to actually make a machine that can predict the age. Okay. For this, I'm not going to be using T1 data nor the output of ANS, because that will be directly the answer to the challenge. But I'm going to use instead some synthetic data that we'll be generating as we go. So here I will start importing packages. NumPy is basically the numeric package for Python. It allows me to build arrays, to build ranges of numbers with precision. And the matplotlib, which is the Python library to plot. Then I'm going to use scikit-learn, which is a Python package that has been installed specifically in this image to do these trainings. Setting a random seed to the package random allows me to generate random numbers in a reproducible manner. So everything that it's done here, even though we call to the random package that it's generate a random number, since we have set a seed to this package,
this will mean that it will be deterministic, so all the results are going to be reproducible. What you typically want to do when you use the random package, though, is to avoid setting a seed, because otherwise it's not going to be random, actually. Okay, so first, just as a brief comment, what I'm going to do here is basically go over the different approaches. I don't intend to explain in detail all of them. There's just simply not enough time. But I want you to grasp the sense of what we're trying to do here, or what it is done by many researchers nowadays when they're trying to build models to actually predict the data. So for what I'm going to do first is basically create a linear model, which is basically create some random data in 2 axes, so bidimensional data, so that we can plot it and show it, and then see the true regression of this. So since this is synthetic data, we have generated from a ground truth regression. So these variables that have 2 dimensions have been created from this regression, adding some noise, some random noise. And what we're going to do is, now that we have only the blue dots and not the regression, the line, we're going to try to infer what is the regression, what is the line that actually can establishes like the connection between these 2 variables. To do so, there are many approaches, but basically what they do is they do procedures that what they do is they try to minimize the error between a specific line and the one that should be given by the real model. So, okay, let me show you the results. So basically what you end up is with a function in Python that what has done is look at the data, try to find the best fit for a line that models the relation between the 2 variables, between the 2 dimensions of the variables, and plot it. So here we have the true line, which is the blue one, the clearly the more clear blue one, and then we have the pink one, which is the one that has been generated automatically. So typically what you will have to do for the challenge is you will have the data, and then you will have to predict if there is actually some model that explains why is this way. So what is the relation between the 2 variables? So what can you infer from the data that we have to predict something? Here we can see other kinds of ways to train this data by building other kinds of models. Okay, I cannot see anything, sorry. Okay. Okay, but obviously the data that we're giving you is not linear. What it means is that it cannot be just simply fitted to a simple line. So in this case, what this notebook shows you, and that you can use to actually figure what functions might be useful to train a model to fit some data, is given some random data that obviously follows some kind of pattern, but it's not linear. How can we train a model to actually predict that? How can we find the function that best fits the data that we have here? And then we have first, obviously, the regression model, the linear one, which is not going to fit very well. Then we have a model which takes a certain numbers of nearest neighbors, which is the k nearest neighbors model, which is basically it tries to find what are the points in a specific local area which average produces the fit that I want. And then we're going to use a simple neural network with multiple layers to learn what is the model behind this. The overall comment on all of this is that different ways of training data can produce different results, obviously, but some of them are more appropriate for specific kinds of data, and others are not so well fitted for. For instance, in this case, you can see that the linear regression obviously is not good enough to describe this data. You cannot just fit a line to this data because the relation between the two dimensions is not obviously a line. If you use the k nearest neighbors, you get what is called overfitting. What it means is that you get a model that depends too much on the local configuration. Whilst if you use, in this case, a simple neural network, you get a model that actually maps what is the relation between these dimensions. Okay. I know that this has been like too short to explain the details of all of this, but I wanted to give a bit of everything to different levels, which is always difficult. But the point is that the material is there, and all these tutorials are out there. If you don't have access to them because you have not copied the link, don't worry, we will send it to you through the mail so that you can have access to all this material. Look at it with time, look at it with calm, and then you will be able to actually know what is this all about. Okay. So since we are running out of time, my plan was to make you do some exercise now, but we'll skip that and we'll just focus on how do I actually work with the SDK, so our SDK, to implement the tool. The idea is very simple. This model that you will have, or this function that you will find that gets some data from the patient and outputs the age, will be a function that you can just input to a Python script that is already to run. So if I go to the container that I had open, which was Awesome Brown, I think, so I attach the container again. Okay, maybe it's no longer there. Vhack, oh no, it's called Vhack. So if I attach to the container where we have the IPython notebook and everything, and I kill the notebook because we don't need it anymore. Okay. We'll see that there is a very simple Python file which is called tool.py. And this Python script is the one that when you launch an analysis and it's executed on our machines, it communicates with the platform, it gets the data, which is the first lines. So you get from the list of input files, you get the one that is a T1, and then you download it to a root folder. Then you have this T1, you can do your processing there, you can use your model that has been trained with the results of ants on the results of cortical thickness, for instance. Then you can run your function that, depending on that data, produces a number, and then you can just put it into a file called output.txt and upload it to the platform. This simple skeleton can be obviously extended as much as desired to create a tool that not only outputs a file, text file, but that outputs some, for instance, other medical images that are in the format of NIFTs or DICOM images, or that it outputs a PDF file with a report or other CSV files. So the idea is that the SDK provides 3-4 functions to communicate with the platform, to fetch the data, do your processing, and then upload it. Okay. Then inside the image, as I said, you will have all the ANTs binaries, all the ANTs programs that produce segmentations, cortical thickness. You'll have all the Python packages for Nylearn, scikit that produce the regressions, the model trainings that I showed before, and that you will find also all the notebooks that I've been showing, so everything is in there. You will have also the Drovex program that it's very useful to perform skull stripping. And you will have the Matrix, which is typically just used for diffusion data analysis, which is something I haven't talked about because Paulo will talk tomorrow. But it can be really handy to convert formats. What? And it can be really handy to convert and everything. And you can see that I put here all the reference links for the documentation for these packages so that you can see what kind of tools you can use to extract data from the T1s. Once you have a container with a tool script that you think that might do something meaningful, you can commit it, that it save it into an image with a Docker commit. Then you can use this script that I attached here to just test it on your machine so that you don't upload something that might be broken. And then here are some notes on how to run it locally. So basically, this is the script that I've been showing that has an input, then has the processing and the output. And in the processing part, it's where you would do your analysis. Okay. I think that this is more or less everything. Now we were to start the Docker files tutorial, but I think that we don't have enough time for that. So I would rather go over what I said, because I know that I've said too many things. Some of them were really simple. Some of them were really too complicated for the time that I had. And I would prefer to go over your questions and see if there is a specific way in which I can help. So, please.
You go back to the where you run the.
Mm-hmm. Inside the container, you mean?
No, just before. You.
Okay, so I'm in a shell. I'm in a shell. You mean? Yeah. Yeah. Tell me.
Now you said Docker run.
Yeah, Docker. So how to start a container? Okay, that specific container for the SDK, you mean? With everything, all the tools. Yeah. So okay, the container is called QMENTA SDK bhack 18. And this is the bit you have to remember. Everything else, you can just infer it from things online. Now, you can download images explicitly by writing Docker pull. And this will just perform the action of grabbing it from Docker Hub and downloading it to your computer. But since I already have it there, it's not going to do anything. Well, yeah, if I had internet connection, now what it would do is it would compare the image that I have with the one that is online, and not directly, but by using instead a hash of the images. And then since it would be the same, it would say, okay, you have the latest one. You don't have to download anything else. Okay. Another thing that is quite important about Docker, and I haven't said, is that Docker images are made of layers, actually. So if I use a Docker image, this one, and I add some code to it, and then I save it into an image, this new image, if somebody else tries to download it, it will not have to download the 6-something gigabytes if it has the brain hack image. It will only download the differences, because Docker uses a system of layers that is incremental. So basically, the layers that are shared between images do not have to be stored twice. This is really obvious when you run any image that is based on Ubuntu, because many of the Docker images are based on Ubuntu. So, which is Docker run Ubuntu. So it's this image, which is basically the basic Ubuntu. It's relatively small. So any image that is based on this one will probably be on any one computer that is using Docker. So when you download somebody's script that has been built on top of Ubuntu, you will only actually download the script. You will not be downloading the whole image, because you have the layer that it's Ubuntu. You only download the last part. And this can be really handy to speed up things, because then you just have to actually store what is different between the images, even though to your computer it seems like you have completely separated computing environments. Any other question? Yeah, please. Sorry. Mm-hmm. Okay. Which operative system are you using? Linux. Okay. And you have Linux installed. It's not a virtual machine. It's a virtual machine. It's not a virtual machine. It is. Okay. Okay. So depending on how you have configured your user, you might need to perform like changes on your permissions for your user. So if you go to getdocker.com, I mean, I cannot just give you the straight solution, which would be just run sudo docker run, because this might work, but it is not the solution. This is a dirty thing that you should not be doing. So if you go to get docker, okay, yeah, I don't have internet. If you go to get docker, you will see that in the installation steps, there is a chapter that says post installation steps. And in that chapter, it explains you how to add permissions to your user to actually run Docker. So you might want to have a different group with a different set of permissions in which you will have to add this Docker. If you just want to run it once for now, you can obviously do Docker run, or at least try it at least once with this, so that you know that it is not your installation of Docker, but rather something with the permissions of your user. So if you just use Docker run IT with the terminal and then Ubuntu, because it's something small that, well, even smaller than this one is the image for the operative system Alpine. Yeah, whatever. I mean, it's not even going to work because I don't have internet, so it's not going to be able to pull it. Anyway, if you try to do it like this, so with the super user domain, that is with administrator permissions, you should be able to run it. Yeah, sure. Yeah. That's the thing. That's instructions that they give in the get Docker thing. You have to add your user to the. Probably you want to create a group that is called Docker, and then you give permissions to that group, and then you add yourself to the group. Yeah. But that might depend on the distribution and everything. So, and the version of Docker that you have also. Sure. Yeah. Yeah, exactly. So the thing is that when I created, okay, let me show it again. So I'm going to do history to show the previous command that I executed. I'm going to write the pipe symbol, which is this one that connects the history with another process. And then I'm going to use grep that finds a pattern. Let's try to find bhack. Then it's going to show me, this is going to show me the list of commands that I ran in the past that contain the string bhack. So here, yeah, I used the P option for the Docker run command because I want the host computer, this Ubuntu, to have access using this port to this port inside the container. And this port is the one that it's going to, it's used by the IPython notebook. So when I was connecting to the IPython notebook, I was using the browser in my host system. It could be Windows or whatever, but I was using a server that was inside actually a Docker. So that is why even if this image has specified that it uses this port, from the outside, you always have to specify if you want to map this port of my computer to this port. This means that you can use Docker to create any server to mock any kind of server online. You can use, I don't know if any of you know Jenkins, for instance. You can use Docker to deploy a Jenkins in 1 second on your computer. And then if you connect to localhost and this port, you will be actually accessing the Docker image. You can use it to actually run anything that is a server. I've seen even somebody running a WhatsApp server using Docker, and then everyone was connecting through his computer instead of WhatsApp. Something not very clean. Any other question? Yes, please.
I have some question about the challenge.
Yes.
Can you come back to the...
Sure. Okay, no, that's useful.
It will be the last question because we are time. We need to be in the canteen at 1 p.m. So, yeah, if you can answer this question after that.
If you want, we can do it first.
No. It might be useful probably for anyone. Okay, I have the slides here. So
18, slide 18.
slide 18. Okay. This one?
Yes.
Yeah.
So you say we have to guess the patient.
Yes.
But I see difference between corporal age and brain age.
About what? Sorry.
Because I don't know if you want to ask the corporal age, the linear age. You know, it's like a philosophy.
No.
Yes.
No. What I okay. So in this case, we will be assuming that the data that has been input in the okay. Just let me explain this properly. So in this project, the brain hack 1000 analysis, you will have all these subjects. All these subjects have this age metadata. It can be downloaded using one of these Python notebooks and everything. And this age was the biological ages at scan. And this is the one that we are trying to predict. Obviously, I know that there are differences, and those differences might be because people that are 80 actually have a brain that is 60 or something like that. But this falls into the noise that it's expected from it. And what we want you to predict is the biological age, which might be also interesting to know, like if it differs more on the later stages of life than in the beginning, or maybe in the beginning people just diverge a lot in their brain age and then just go all the way to the same point. But no, in general, what we want you to predict is this value, which is the biological age at scan, at the day of the scan. Yeah. Yeah. Totally. It's not going to be on the same age, obviously, but it's going to fall under narrow noise. I mean, this subject is from healthy patients, and all of them have been so all of them are not representative that much of the whole population. And the only thing that we can tell you for sure is that around 5% of them are clearly different, and they have Alzheimer's disease. And that if you find an outlier or something, that's probably because the atrophy is coming from Alzheimer's disease, not because that people was on drugs. You can just skip that. We cannot just take from the population itself. Yeah, it's a clean data set. Is this the question you were?
Yeah, but
kind of. There is a variability. That's for sure. But in general, biology and time has its weight. So even if you are super healthy and everything, the thing that we say about having a brain of 20 whilst being 80 is not that true. Like there are really things that change through time.
It also can depend on the knowledge of a person. Maybe if I have more knowledge than other person, I can have.
Yes, but even like in this case, we are not going to like enter psychological realm or anything. We'll just like be on a more pure anatomical from the outside study. And I know that this can have implications and everything, but I wouldn't overcomplicate this that much in this case. It's a nice discussion, obviously, but and it would be super nice to have a study that tries to find these kind of correlations to see what kind of lifestyle actually translates into what can be inferred from the outside. But in this case, we're not trying to tackle that. Okay. Thank you very much.
Just two questions. I don't know if you are having troubles connected with internet.
Maybe just my computer. I mean, I was using it today, but maybe it got fried or something. I don't know.
Anyone? Nobody having troubles? Okay. Because maybe for download datasets or whatever, we'll need more powerful connection to work together. Okay. Just for the lunch, you have to keep your ticket. I think all of you have a meal ticket, right? You don't know what is the